Chapter 14, chemical kinetics, is all about rate of reaction and things that affect rate of reaction. So consider the following graph of the concentration of a substance over time. Is X a reactant or a product of the reaction? Okay, so we're starting with no concentration. As time goes on, the concentration is increasing. So this tells us that X is a product. So we're measuring rate of reaction here as to how fast X is appearing. B, is the reaction speeding up, slowing down, or not changing its rate as time progresses? The slope of this line gets less and less as the reaction goes on. So looking at these time intervals, we have a steeper slope at the beginning. All right, so as for the same amount of time, same increment of time, I have a more drastic increase in concentration. As time goes on, it gets shallower, so it's slowing down. Why is the average rate different between points 1 and 2 than between points 2 and 3? Well, it's like we just said, right? The reaction is slowing down. The production of X is getting slower and slower as the reaction goes towards its end. So rate of reaction is defined as the change in concentration over change in time. So if at the same time interval I'm getting a more drastic increase between points 1 and 2 than I am between than a change in concentration between points 2 and 3. So a shallower slope means a slower rate of reaction. You study the rate of reaction measuring both the concentration of the reactant and the concentration of the products as a function of time and obtain the following results. All right, so what's happening here, as the concentration of B goes down, the concentration of A is going up. So this tells me that B is a reactant and A is a product. So which chemical equation is consistent with this data? Well, A is a contender, right? No, A isn't a contender, right? B is a contender. B turning into A, right? So B is a reactant turning into A. So B is a possibility. C is not a possibility. D is a possibility, and it's the best answer. What's going on here is, as if you look at these curves, as you get a certain concentration change in B, you're getting a more drastic concentration change in A. So what this represents is, for every 1 mole of B disappearing, 2 moles of A are appearing. So D. If you perform a series of experiments for the reaction of A turning into B plus C and find that the rate law has the form rate is equal to K times the concentration of A raised to some power, or that's the definition of a rate law, determine the value of X in each of the following cases. All right, so a rate law. Rate is equal to change. What you're doing with a rate law is you're equating change in concentration to how it affects the rate, and you need some constant that equates the two. Now, when I look at example A, there is no change in concentration, no change in rate of change when the concentration of A is tripled. So what this indicates is what's called a zero-order relationship, meaning the concentration of A is having no effect on the rate of reaction. So putting more of it into the reaction doesn't make the reaction go any faster. So that's what it means to be a zero-order relationship. Raising anything to the 0 power is equal to 1, which is a no change for the rate. B, how does the rate increase? The rate increases by a factor of 9 when the concentration of A is tripled. All right, so in this situation, A is having an effect. Now, doubling the concentration or tripling the concentration isn't tripling the rate of reaction, it's having an exponential effect. So if I take 3 and square it, that's when I get a 9-fold increase in the rate of reaction. So this is what's called a second-order relationship. Triple the concentration, it's not going triple as fast, it's going 9 times as fast. And for the last one, C, when A is doubled and the rate increases by a factor of 8, what's the relationship? Again, this is an exponential to the 3rd power. If I double the concentration of A, it's not going twice as fast. It's not going 4 times as fast. It's going 8 times as fast. So this implies a third order relationship. Taking the concentration, raising to the third power, this is how I get an 8-fold increase in the rate of reaction. 6. The following diagrams represent a mixture of nitrogen monoxide and oxygen. These two substances react as follows. All right, 2 moles of nitrogen monoxide reacting with 1 mole of oxygen makes 2 moles of nitrogen dioxide. It has been determined experimentally that the rate law is second order with respect to nitrogen monoxide and first order with respect to oxygen. Based on this fact, which of the following mixtures will have the fastest initial rate of reaction? Well, with the one with the highest concentration of the reactants. All right, so nitrogen monoxide is the blue one matched up with the red one, and the 2 red ones together are oxygen. So that's compartment number 1, right? This has the highest concentration of, well, all right. Nitrogen monoxide, right, has an exponential relationship. So you want more of that in the mixture, right? That's influencing the rate the most. So looking at number 1, when I count them up, I've got 1, 2, 3, 4, 5 nitrogen monoxides and 1, 2, 3, 4 oxygens. So when I plug these into the rate law, I get the greatest increase in rate. Be a 100-fold effect. Right? Again, we're ignoring the rate constant here. The rate constant would give me the actual rate, but this is going to have having these concentrations, I would have a 100-fold effect, and with the other ones it would be less. A friend studies a first-order reaction obtains the following 3 graphs for the experiment done at 2 different temperatures. A. Which 2 graphs represent experiments done at the same temperature? What accounts for the difference in these graphs, and in what way are they the same? All right. This graph is plotting the natural log of the concentration of A versus time. This relationship is gotten by integrating a first-order relationship, right? So they told me it was a first-order rate law. So if I double the concentration of A, I double the rate. So if I integrate this function, I get this equation. Now, this is an algebra class. You don't have to know how to do calculus here, but you do have to know how to plug into this equation. So the integrated rate law for a first-order equation equates the natural log of the concentration at time t equal to negative kT plus the natural log of the initial concentration. All right, so this is an equation for a straight line, where m is the slope of the line. So k is the rate constant, so the slope of the line is represented by the rate constant. If I have a steep slope, I have a fast rate. If I have a shallow slope, I have a slow rate. And I'm equating it to time, right? So this is a very powerful equation. If I know what the initial concentration is, and I know how much time's gone by, and I know what the rate constant is, I can figure out what the concentration is at time t without doing an experiment. I can just plug into this equation. All right, back to our problem, right? They want which two graphs represents the experiments done at the same temperature. Well, at the same temperature, you're going to have the same rate constant. There's a relationship between temperature and rate constant. We'll get to that later on. But for right now, if you increase the temperature of a reaction, you speed it up. If you look at the rate law, you're not changing the concentration. So what you're changing is the rate constant. So a big K, fast rate, small k, slow rate. So 1 and 2 have the same slope of the line. So line 1 and line 2 are being done at the same temperature. Now they're starting at different places, right? One is starting at a lower concentration than the other one is. So that's the difference between them. But since the slope of the line is the same, they're being done at the same temperature. All right, B, which 2 graphs represent the experiments done with the same starting concentration but at different temperatures? All right, so that's going to be 2 and 3. You're starting at the same concentration, but 3's got a shallower slope, so this must be being done at a lower temperature, whereas 2 is a steeper slope, so it's being done at a higher temperature. Which of these graphs represents the lower temperature? Right, number 3, the shallower slope. Shallower slope, smaller rate constant, slower reaction. Oh, there we are in writing, right? Experiments 1 and 2 are occurring at the same temperature. Okay, they have the same slope. If we're looking at experiments 2 and 3, they're starting at the same concentration, but 3 is starting at a lower temperature.